let's look at the inclined plane again, make sure we understand how to find the net force and answer the questions of whether we're moving up or down the plane and whether or not we're accelerating or not. In the beginning, as you start to learn this material, it's okay to keep a calculator on hand and use it because it's difficult to make up problems to practice where the numbers don't require a calculator. They'll do it for you. When you take the SSAT, the numbers will be easy. You won't need a calculator. But I don't always stop and make the numbers easy. So in this particular case, I kind of picked them at random. With an inclined plane at 20 degrees, the sine and cosine of 20 degrees are written here. The tangent is that. And I gave you a test in the last video. Make sure you understand it. A test in the sense of something to use. That if mu is less than the tangent of theta and the static mu is 0.8, it is certainly not less than 0.36. So there's no motion. The static friction keeps this block from moving. What do I have to do to get the box moving? Well, in order to get the box moving, I need to have an F net of 0. I need to just overcome the friction that points up the inclined plane minus the parallel force. So pointing up the inclined plane, I have 0.8 times mg cosine theta. That's around 141 newtons. And I have mg sine theta pulling down the plane in the vicinity of 51 newtons. So there's a delta of like 90 newtons. Whatever the difference is in those two, that's what you must push with to get the box moving. So it's easy to write the F net to get the box moving because F net will be 0 when the box just starts to slip. So if the box is moving, we're on this mu now. So the parallel force for moving box is going to be the same, mg sine theta. That's 150 times sine of theta 0.34. So, and we'll just use the calculator to make it go fast. 153 sine, 150 times the sine of 20. And again, that's the 51 newtons. But now what is the box pulling back with? Well, it was pulling back with the 0.8 times mg cosine theta. Now it's a quarter of that. So it's pulling back with about 28 newtons. Once I get the box moving, I have a net force down the plane of 51 minus 28, which is 23 newtons. And that'll equal MA, where mass is 15. So dividing 23 by 15, we're going to get about 1.5. So with these numbers, when you look at it, 0.8 is bigger than 0.36. There's no motion of the box. To make the box move down the plane, you have to just balance whatever the difference is between the static friction coefficient, opposing motion, and the parallel force, causing motion down the plane. And we figured out that we needed to give it a push at 23 newtons. However, if we don't immediately withdraw that, in fact, if we do withdraw it, it's the friction force that's kinetic isn't enough to keep the box from running away at an acceleration of 1.5. If I want the box to move down the plane with constant velocity, I've got to make sure that the 51 newtons is balanced by friction. So instead of having 28 newtons up the plane, I need 15 newtons up the plane, to balance it. So I write my F net. I want to be 0. And we did this. We had acceleration of 1.5. We'd like to back off to 0 and make the net force on the box 0. So F net is F parallel, that's this force, minus the force of friction. So the parallel force down the plane was the 51 newtons. and the frictional force is 28 newtons. And so the difference between those two is what I have to provide now. It's 23 newtons, right? So I've got to now pull. I have a net force of 23 newtons, creating that 1.5, as we found. So I need to add that 23 newtons of retarding force, so I get an F net of 0. So this one's 51, and I'm going to have to make my F pull up the plane, which makes it negative, to the tune of 23 newtons. Now I'm balanced. My down the plane force equals my up the plane force. F net is 0, meaning the acceleration is 0. When A is 0, the change in velocity is 0. So when the acceleration is 0, the velocity is constant, not necessarily 0. And those are all the cases for the box moving down the plane. The box won't move down the plane. You start it moving and it accelerates down the plane, and it accelerates at 1.5 meters per second squared. You figure out from F net being 0 to make the acceleration 0 that you need to provide another 23 newtons acting up the plane to cause F net to be 0. Now you have constant velocity down the plane. Moving up the plane is just as easy. The problem is that the SIG and S signs, not to be confused with sine of 20 in trigonometry, but when I start to pull up the plane, this becomes the positive direction. So F net has some sign changes taking place. And you definitely, we noticed that the static friction force kept the box from moving up the plane. So we would definitely have to exert some force to get the box moving up the plane. And we'll have to overcome the kinetic friction once the box is moving and the parallel force. Those are the two forces that act down the plane when the box is moving. We have a mu kinetic stopping the box, and we have an F parallel stopping the box, and our F pull has to be enough to overcome those two. We can calculate what those are. We kind of already know those numbers. We know that the kinetic coefficient of friction acting down the plane, the kinetic friction was 28 newtons, and the parallel force was 51 newtons. So if we pull with just enough to overcome these, 51 and 28, 79 newtons is our F pull. That gives us a net pull up the plane of an acceleration of 0, which means that the velocity going up the plane is constant, provided we pull at 79 newtons, which overcomes the two forces that try to stop the motion, the friction opposing you and the parallel force due to gravity, and the fact that gravity acts straight down and we're working on an inclined plane which is tilted relative to gravity by theta degrees. What if I pull more with 79 newtons? Where does the extra pull force go? It goes to F net not being 0 and going into MA. So anything above 79 newtons shows up as acceleration. Suppose you want an acceleration of 1 meter per second. Well, that's 1 meter per second times the mass of 150. So 150 times 1 is the extra amount of pull force above 79 that you need to produce 1 meter per second squared of acceleration. So if you want 2 meters per second of acceleration, mass is 15, not 150. So 15 times 1 in addition to the 79, for every extra 15 kilograms of pull I put in above 79, I get an extra meter per second acceleration. Because just to hold the box at constant speed takes 79 newtons. Every extra newton above that goes into MA. So if you tell me what you want for A, and I'll tell you what to pull with. Suppose you want an A of 3. Well, that means 3 times 15 is 45. We need 45 newtons in addition to 79. So 45 newtons in addition to 79, you'd better pull with 124 newtons. So it's relatively easy to calculate what to do if you draw this picture, decide whether you're moving up or down the plane, and calculate your F-net accordingly. F-net should be what value for constant velocity? If I want constant velocity, F-net should be 0. So I get an acceleration of 0, a delta V, a change in velocity of 0. When you're moving up the plane, the calculation's pretty easy because you calculate the parallel force caused by gravity and the kinetic friction force. Add those together, and that gives you what you need to get in to overcome those pull forces. Anything extra goes into MA. Pull with 79 in this particular case, move up the plane at constant velocity. You want to move up the plane at 12 meters per second squared, 12 times 15 plus 79. The 79 just gets you in the game. It's sort of like the cover charge at a bar. Not that you would go to a bar ever, but in case you did. You have to pay a $10 cover charge to get in. That's just to get in. Oh, you wanted to enjoy the show and have something to eat? That costs more. That's what you put into MA. So hopefully that puts to rest for right now some of the issues associated with the inclined plane. You should practice a few of them yourself and think about this. Maybe you want to watch the videos again that have to do with motion on the inclined plane until you're satisfied that you understand the directions, the SIG and S signs, and what to do with sine and cosine to calculate the 3 equations of importance. The friction force, whether it's static or kinetic, that's one force. Then you have the parallel force acting down the plane due to gravity. And then you want to have your pull force acting either up the plane or down the plane. Remember, in what direction does friction act? Wherever F pull doesn't. Friction is the one that fights you all the way. Okay, I'm a lot happier with that subject now, if you study it, that you could get through these. And don't forget your quick and dirty check. If the question is there motion? If the coefficient of static friction is less than the tangent of theta, then there is going to be motion. 0.8 was not less than 0.36. We had to push the box to get it moving. Okay, think about this, do some practice problems, and we'll move on from here.